Just want to give a little graphical depiction and hopefully a clarifying description concerning the photoelectric effect and how it could be useful to us analytically. So here you can see sort of a depiction of a Bohr diagram of an atom with first energy level, second energy level, third energy level, fourth, and then here I'm representing this gray band as being where it ends to the right is the outer edge of the electron cloud. And my formula up here in the red box is saying that the kinetic energy of an electron that got ejected because it absorbed some light is going to be equal to the original energy of the photon of light, the packet of light that hit that electron and was absorbed by that electron, minus this funny Greek symbol, which is representing what we call the work function. But the work function, we're saying, is equal to how much energy it takes to go from that energy level where the electron was out to the edge of the electron cloud. And so here we're saying this is kind of another graphical depiction of that equation, only we've lined up the subtraction and its difference vertically. And so here, this tan band, this tan bar here is supposed to represent how much energy there was in the photon. It's supposed to represent the amount of energy in the photon that hit the electron. And then this Greek symbol with the subscript 4 is supposed to represent the fourth energy level work function. So if an electron was in the fourth energy level, how much work would have to be done? How much energy would have to be spent just pulling the electron out of the electron cloud? And then the rest of that energy is left over as kinetic energy of the electron that got ejected. And so you can see as the amount of energy required to just remove the electron from the electron cloud increases. So from energy level 4 to the edge of the cloud requires less energy than from energy level 3 to the edge of the cloud, which requires less energy than from energy level 2 to the edge of the cloud. And as the amount of that required energy, that work function, to get the electron out of the cloud increases, so then the kinetic energy left over for the electron as it travels, as it leaves, is going to be less. So let's go through them individually. Here I've lined up that bar that represents the total amount of energy available in the photon that gets absorbed by the electron from the fourth energy level. And you can see we spent this much energy just getting out of the cloud, and here's how much kinetic energy is left over, quite a bit. That's for the fourth energy level electron to get out. For the third energy level electron to get out, we're still using the exact same kind of photon with the exact same amount of energy per photon or packet of light. But now, since it took more energy to get out of the cloud, less energy is left over in the form of kinetic energy of the ejected electron. And then when we get to the second energy level, you can see that the amount of energy available in the photon is not even enough to get to the edge of the electron cloud. It's less than what it takes to get to the edge of the electron cloud. So the energy of the photon is less than the energy required to get to the edge of the cloud. Therefore, the electron just won't be ejected. It won't even get out of the cloud, and it won't have any kinetic energy as an ejected electron. So that's why that says kinetic energy of the ejected electron is 0, because it doesn't even get out. And we wouldn't even bother talking about applying this size of a photon to a first energy level electron, because that would clearly not be enough to get it out of the cloud. And in this case, you can see that bar is not even enough to get us from the first energy level to the second energy level, so it wouldn't even cause an electron transition inside the electron cloud. But again, our topic here is getting electrons out of the cloud and how fast are they going when they leave. So let's consider a different scenario. What if I had a photon with way more energy in it? It might be a photon from the far UV, which means it's not that close to the visible range of the electromagnetic spectrum. Or maybe it's an X-ray even further from that part of the electromagnetic spectrum that we can see. So clearly this photon here, represented by the large, long tan band, has plenty of energy to even get a first energy level electron out of the cloud and still have some kinetic energy left over. And of course, then if you apply such a photon, far UV or X-ray photon, to a second energy level electron, as is depicted here, even less energy was required to get out of the cloud. The work function was even smaller. So therefore, the kinetic energy is going to be even bigger, and so forth with the third energy level, and so on with the fourth energy level electron getting ejected. So we would expect electrons to come out much faster in this case, because every photon that was hitting any electron had far more energy, and we'd even be able to get some first energy level electrons out. So using these kinds of photons with plenty of energy, any electron that gets hit by one of those photons will get ejected from the electron cloud of the atom. And then we can do some analysis with that, which will be what we'll talk about in the next video.